start from here. And the following stuff is just some shell script, and it's very easy. Just define some variables and to run the Matlab here. See here, if mat down, you can search what is mat down. I'm gonna tell you something about the Vim. Just press a hash symbol here. It can highlight all these symbols variables. Mat down is just iOS star RYG. It means if this directory contains RYG mat, it will do this. Else if alt down is defined here. Output appendix, which is alt.h file. If it contains this, we do this. So you can go through it, and I can tell you the conclusion. Conclusion is if one directory already contains in.h file, alt.h file, and ryg.mat, those three kinds of files, this script won't do anything. And that means if you want to set up a new simulations, you should choose a new directory rather than put the original data directories here. This is just the shell command to run the Matlab. So the Matlab single computational thread means we only use one computational thread without any GUI, no display. And go to that path. We add a path, add this directory, this path to the Matlab's path, and then we go back to the PBS working directory again, do the same thing for the path 2, and then we go back again, go to the data directory. This is where we will output, the code will output the alt.h file files, in.h file files, and then we run the, here is post process, here is the pre-process, and this is the files, the function's argument, this PBS array ID and the output files. This array ID, I'm going to talk about this here. The array ID is also a keyword in the PBS system. If you use this -t, this PBS-t 1, 2, 3, this PBS array ID, this keyword will give you a vector from 1 to 3. If it's 1 to 100, it's 1 to 100. Just give you a sequence of vector. Just give you a vector, and it's just some number sequence. And you can do those array ID whatever you want. We will see how Yifan use it. Okay. So wait a minute. In this SpikeNet directory, this Matlab interface, the cases, and here the Yifan's cases contains all his pre-processing functions. We're going to use a reference, maybe this one. This var argin is, it means any arguments you want to input to this function. And here we can see in the PBS script, we give this pre-processing function an argument, this PBS array ID, which I told is from 1 to 3 in this case. So in each time, it equals 1, 2, or 3. For example, if we in the first trail, then this guy equals to 1, and then we can see where it appear again. We use Control F to find this variable. So it gives a PBS array ID and put this, if it is array ID doesn't equal to the loop number, it will continue. Basically, before this array ID control system, there are so many for loops. The for loops is to sweep parameters. For example, if I need this P0, whatever this variable is, from 0.01 to 1, maybe it's too large. Okay. Then this, if all others variables all equals only have one entry, means all these for loops will iterate this a 0.08, 0.09, and 0.1. Okay, let's go through 3 times. So each times it will go through everything under those for loops, and when this loop number, which is a container to contain the loops, the number of loop. So if loop number doesn't equal to PBS array ID, it will continue, means doesn't do the following stuff. So when the array ID equals to 1, and this loop number is to 1, and do everything. If this guy is 2 and this guy is to 2, it will do everything. Otherwise, they won't do anything. So this is the way to use the PBS array ID. It basically just to sweep all the parameters. Do you have any problem here? Yeah? Yeah. Okay. Okay. What else I should? Already have structure. Yeah, structure. We move to the structure of main function. Okay. Before this PBS array drop control system, all these for loops are parameters. You can give those parameters. You can play around with them, set up different parameters if you want. And after this, we will put those parameters in the in.h files. For example, the first one will generate when you want to see something, you'd better put this SpikeNet on your path, selected folders and subfolders. Okay, and we go to this guy, have a look. Some basic subroutines, Yifan already annotated them in detail. See this one. This is data now. Give us timestamp. This is a name. Basically, it's a loop number, which is the array ID. Just for example, if the array ID is 1, here is 001. See where here. And plus this data now, and give a appendix -in.h file. This is the file's name. So every file is named by this rule. First is the array ID, and then the time is generated, and then the in.h file. This is the name rule. Here is the code to generate those HDF files. Okay. And then we go to write basic parameters. This FID, see, we need this FID for all following subroutines. We go to here again. Let's see, FID, DT is a simulation step, and the total steps. N is the number of neurons. See here, and just put these things in the in.h5 files we just generated. Yeah, and keep going. This is where to change the spike frequency adaptation. If you want to know what it is, just go to check Yifan thesis. Spike frequency adaptation, and this guy is a flag. If it's 1, we will run this. Run this means write those relevant parameters to the in.h5 files, and then C++ simulator will know it, and then we'll do the specific calculation. If it here is 0, then it didn't do anything. Okay, we'll keep going. This is population, write population parameters. For each subroutines, you can go to check what is the meaning of those parameters, and if it's not annotated, you can check how it's used in the code. For example, if I don't know what is pop index, just find this. See what here? Because this part is because the C++ start from 0, so it's -1. See, basically just use it here to write this thing. This is HDF files structure. HDF files is a structure, hierarchical data structure. I can give you smallest instruction. Okay, it's like this. If this is a name of this HDF files, and then it will have some like a tree. For example, this is A, B, C, and here is A1, A2, A3, and this A1 go further. A small A1, A small A2, and it can go further. This is a HDF5 data structure. So here this directory, see here, means in this HDF5 files, the A equals config, the A1 actually is pop, is small a1 is a parameter, this guy here, right? So this directory just means the tree structure, right? That is the address for this tree. Okay. Go further, keep going, and write external current. Actually, it's not current. This annotation is wrong. It's external specs, as it's named. There are two kinds of stimulus in this model. The first one is specs. Another one is current. Let me specify here. Probably go to his. Could use this differential equation here. And enlarge this a bit. Okay, this is the basic formula, differential equation for the integrated and fair model. It's just like you treat each neuron as a IC circuit. CR circuit. This is a capacity, and this is a resistor. Okay. This is R resistor. And then, do you remember the differential equation for the capacitor? It's du dt equals to I, if I remember correctly. So integrated and fair model is just this, very simple. Just use this way to replace this U, so becomes C is capacity, this is membrane potential, or you can call it voltage. The dt is a time. I is a current. So current equals to V or U. We use V here, right? The voltage over capacity, or we can write it as conductance times V. So this is conductance, this is V. Because you know the voltage is a relative physical value, so you have you need a base to represent the real voltage, the membrane potential. So this is just the base. This is a base for the leaky part of this integrating neuron. This is excitatory reversal potential, which is also another base. This is an inhibitory base. So every this component has its own base. Right. Clear here. See. Right. Okay. So if we want to add the stimulus, so we can just directly add after this differential equation. Stimulus. Right. This can be one kind of stimulus. Another kind of stimulus is based on the coupling structure of these neurons. See here, this conductance formula, it means if this is a neuron and it receives several neurons signal, once this, let's call it A, once this A neuron spike, this is a delta function here, it will add something to here. It means if this A neuron fails, it can increase this neuron's conductance. So now, based on this coupling structure, if we add many Poisson neurons means these neurons' spike history look like a Poisson process. It keep fair like a Poisson process, right? Keep fair. One bar means one spike, and then we put this Poisson neuron as the input for the neuron we are considering. So this is the second way. Is use the spikes as the external stimuli. Build some Poisson. Maybe you can use Gaussian neurons, other neurons, if you like. In this context, we use Poisson neurons. Okay. There's two ways to add stimulus to this model, as far as I know. Okay. Let's just write the external specs. And if you look into this subroutine, you can see what is the strength of the external chemical connection. Means what is how strong this connections coupling strength is. And what is the spiking rate means what is the Poisson rate of these external neurons. Okay, and what which neuron received those Poisson neurons output is defined here. Neuron logical vector turn if the neuron receives noisy input. In this model, if you want to show some dynamics, you should give a background noise. Otherwise, this network doesn't have a drive. So the driving force is the external noise. So now we input some external specs to drive this neural network. When you set up the stimulus, also use the same way. Just you may use some heterogeneous, because now I give a homogeneous Poisson neurons. If you give specific heterogeneous Poisson neurons, just give some neurons, or just give those neurons in certain period. In this certain period, it can receive those stimulus. You can set up all those things based on this function and also another function called ret external specs tam. I don't know what's the inv, but anyway, it's just a function to give a temporal heterogeneous stimulus. This one is give a spatial heterogeneous external pattern. If you want to use current, there are ret external current setting, ret current external current population, ret external. Oh, another third method is external conductance. Yeah, I should let you know this as well. Conductance means this guy is conductance, right? We already explained this, and also this guy is a guy for these two variables. This if is the external conductance. See here, the external input. If we directly give this here, it's also the third way to input some signal or stimulus to the network. That's the third way. Okay, and if you have time, you can go through all those subroutines, check all those annotations, see whether it's useful for you. Okay, then we skip all these things, the other things, skip them and go to here. Here is another important part. This neuron sampling here. That means if you want to know or save some neural data after this simulation done, you should call this function. See this data type. Data type is a logic vector. See the logic vector for V is the membrane potential. I dash leaky is leaky current. This is amper current. GABA current means excitatory current, inhibitory current, and another synapses current. We didn't use it here. Did we use here, Yuxi? NMDA? NMDA. In Yifan's model, did he define the NMDA?
Yes, he defined that, but he never used that.
Okay. I also don't know what's this. So that's why I don't recommend you to learn SpikeNet, because Yifan maybe know 95%, and I know 80% of he knows. So you know 80% of I knows. After 3 generations, nobody knows everything. Okay. This is the external current, which we just input if we use the external current subroutine. This is a potassium current. Potassium current is I think is for spike frequency adaptation. I also don't know what's this. Okay. If you want to know this, you have to go to C++. If you are interested in, let me know. I may check this for you. Okay. This another thing very important. If you want to know those variables such as membrane potential, currents, those things, you should call this function. Otherwise, the simulation will not save those variables to save the memory, save the storage, because could be very large, and you can specify which neuron, which variable you want to sample, and in which time period. Okay. Another thing is in his main function, he used I think this guy. He sometimes he will save some variables, like in this function, he sees this in degree mat several stuff, and it may be useful for you, maybe not. So don't care too much. Okay, that's all. That's all for the main function. So any questions? Once you don't know anything, what's the meaning of the variable, just use, for example, I don't know what this. I just search this guy, find this guy, where is it? And it comes here, and then we keep searching this guy. Okay, that's the way to find out the variable's meaning. Yeah, then he put it to k, and we check what is k. Maybe k too much k, they just choose whole word. Yes, he put it k in this right chemical connection HDF file. Okay, then we go to the definition. What's wrong with this k? And then you will know what is k. Okay, let's just tell you the way to find out all those variables meaning. Okay, k is the synaptic connection strength vector, and then you will know what is k dash mat and what is j dash ei, and trace back. Okay, see what. So use the method I just said. I believe you can figure out all the meanings and what all the subroutines function. If you still don't understand something, you can do this. For example, I would like to see what's this JEI. I just give a breakpoint here and run it. I don't know what JEI. Let me see, find here. JEI equals to this guy. Just double click this JEI will show use value. So Lucina, your question is what is the range? Just set up a breakpoint, and then you will use the min and max function. Then you can know the range of the variable. Okay. That's some basic things you should know. So any questions? So far, so good? Okay. Okay, how to read code. Seamless tell you that your output file. Okay, then we go to the output file. What is the structure of this ryg.mat? There is this guy, ryg.mat. What is the data structure of this guy? Then we'd better go to. So now I'm going to log out dance account. Go to my account. Unfortunately, the recorder didn't save the install initialization part. Anyway, this is a directory, some output files I got. It's all.h5 files. Then we load it. A way to find out files in a Matlab directory is dir, this built-in function. Say I use d equals dir, use star symbol to represent all strings. See ryg.my. See here this command. I can show you here this command, and then you can see what is D. D contains 491 struct. Each one has a name of those functions, and also what the folders, data, bytes, is directory, date number, lots of these fields in this structure. So what we need is only this name. So it's very handy when you do large data analysis. So we know we load the first one, we just the one name. Okay. What is R is all fields. R is a struct, just as this ryg.mat, and it has so many fields. I'm gonna go through some of it because maybe not everything is useful. Before the explanation of this structure, let's go to see this post-process function again. First, yeah, he did the same thing. See, find out the out.h file and then read in. Let's go through it together. Just use the technique I just said. And then he use a file, this cell, to save all the name, and then maybe he will load it somewhere. File name, files, use files again. I guess this file was written by Yifan when he first do this, so it's not so efficient. Files. Read each file. See, finally I find out a subroutine to read these HDF files. We can go into check it. What is? The files are cell array of char array defining the path of input files. If given no argument, it search for match under current directory. Okay, and out file out.h and do what? File directory in all data. Yeah, all data is read out. This read each file will output. The stamp. What is stamp? Stamp is maybe the file directory and file name. So you know you will know what is R stamp it is. Stamp. See, this is R stamp. It's generated by this guy. This guy here. See. So if you want to know everything about the RYG's subfields, you should check out this post process. See what is this is DT, what is number of population means, what is spec hist, what is number of spec, what is number of refractory maybe, what is population parameters, what is this, what is that. Just check this function. It's very, very long. So I'm gonna tell you something you may need. For other details, check that file by yourself. This R.analysis contains frame rate. The Hertz dash overall is averaged frame rate of all neurons, including excitatory neurons and inhibitory neurons. And this hz.t has two cells each represent, I think it should be one is for excitatory neuron population, another one is for in vitro neurons. And same way, the read is also for, see, we have in Yifan's model, I'm gonna briefly explain this. It's like this. If this is our grid, it's 1, 2, 3, 4, 5, 6. Actually, it's gonna go to 36, and it's gonna go to 36. Okay, on each integer grid point, here has excitatory neurons. All this here, cross point has a excitatory neurons. Means we have 63 by 63 excitatory neurons, which is, yeah, and you will find it exactly equals to the number of atoms here. So that means wherever you see this number, it contains some signals for the excitatory neurons and for each excitatory neurons. For inhibitory neurons, they are randomly distributed. For example, use another color. Maybe use green. No matter it is integer grid point or not, it's randomly located. And we have totally 1000 excitatory neurons. So this 1000 neurons is here, this guy. Okay. The rate, and then we can see, oh, this rate is, you don't need to care about the rest. The rest is defined by me, because you also can revise that post process and add some features, remove some features for speeding up, or for example, I add this spontaneous rate and evoked rate. You can do them by yourself, yeah, as well. Add more subfields. It's up to you. So that's analysis. And then we can go to see the RFP. RFP is the local field potential. If you check, I checked Yifan C++ code, is the algorithm for this RFP is very artificial, because in the neuroscience field, nobody knows how to simulate the LFP accurately. So everyone uses approximation. His approximation is like this. If this is a grid points I said earlier, and I set up electrode. If the electrode is here is the electrode, then this guy will collect in some certain range, especially, and will collect all those neurons, excitatory current and inhibitory current. For example, this neuron, all these neurons, maybe also include inhibitory neurons. Collect all those neurons current, and then use a Gaussian filter smoothly. That's LFP. Okay, this may be useful because sometimes Pulin will ask you to reproduce some experimental data. You may need this LFP. LFP contains LFP neurons, so which neurons the electrodes covered, and what is the real LFP signal is in this. In this r.lfp.lfp, it also contains 2 cells. It's a number of electrodes times steps. So I only use 2 electrodes now. So in Yifan's case, he may use more 13 or 9. I don't know. Check the code in the corresponding area. I guess it should be here. Just search in his main function. Search LFP. This LFP sampling here. LFP here. Currently, I suggest you don't change this part. Just use his default setting. After you figure out all the algorithm, you can change by yourself. These are RFP. Okay, then we go back. All the other stuff is added by me. Some gamma, wavelet, FFT is added by me. I would like to run all my post analysis in one script, so I did those things. In the default version, it doesn't have. So okay, and it's another thing is this spec hist. Spec hist is spec history. Like I said, the 3,969 is the number of eccentric neurons. So it's for every eccentric neuron. If it is paired in this time step, it will have 1. If not, then it's 0. 1,000 is for implicit neurons. This guy is maybe the most variable you need. The most useful variable you need. And maybe also the pulp state. For some of you using my version of SpikeNet in this R.grid, it contains some subfields to save the central mass of patterns. I use CHIS, this population vector method, to characterize the pattern's location, and I put everything in this directory. What is the center? Center is x. 2 is for x and y. 10,000 is for 10,000 millisecond. And what it means that was the adding window, the jump window. If you want to know what's the variable meaning, check my code. I think it should be what? Maybe I can find here. Get grid varying center population vector. Get grid varying center population vector. This algorithm only can be used when in your dynamics the pattern is always appear, because sometimes the pattern may disappear. Then this algorithm can't work. So when you use it, it means you always have a pattern. Then you can use this algorithm. If you want no details, check this thing. See here, I define the center, bin size, sliding window, jump size, all this stuff. Okay. So for example, if I would like to visualize this guy, the dynamics, I just plot, visualize the grid varying center -GC. GC is my name. R. The algorithm is pulp. the red cross is the center of mass, and the black and white image represent the number of specks in this grid point in certain time window, maybe 5 milliseconds. So because in my case it only contains one pattern and it always appears, so I use this algorithm. You can visualize it and also can do some analysis. Okay. Visualize dash grid dash variance center dash GC.
So what's the red cross then?
What's the what?
What was the red cross just then?
A red cross is center of mass. Center of mass. Yeah, center. COM. Okay. What else I should tell you? Oh yeah. I recommend you to learn NIST or Brain 2. It's all developed by Blue Brain project. Chen is the guy in our group who is using Brain to, and also you are using NIST, right? Mm-hmm. Yeah. And I think NIST and Brain at least have better documentations, and they have forums. You can ask questions there, and you are able to know everything. But for SpikeNet, I don't think you can know everything. So I highly recommend NIST and Brain 2 if you want to do more in this field. Okay, the last but not least is I will give you a brief introduction of this C++ code part, because sometimes you can't know when you can't know what's the variable's meaning or what is the algorithm, what is the detail. The only way is go to the C++ code. It's the only way because it's not well documented. It's a main function. So in C++, every time when you call this simulator, it will go through via main function. So main function is kind of like a saved keyword, and you can see here first it will import the HDF files. This HDF file is one that pre-processing Matlab function generated. First, import this thing, and you can use this some editor. Like me, I use the Sublime. I just put my mouse here, and they will see definition. Here I just click. It's at simulation interface.cpp. Here is import. In HDF file, it contains everything. So this is the position of the tree, and read this vector from the HDF files, and read lots of parameters in. That's all. And after that, we are going to do the simulation here. The simulate. Click simulate, and then you can see. I think Yifan C++ code is okay. It's readable. If you need to know more details, check his C code. And the basic structure is like this. It has 3 classes. The first one is neural net. Neural net is class to contain all parameters for this neural network, and it also has 2. First one is called neural pop class, and another one called chemical sense. So this guy contains the coupling strings, those chemical connections. This guy contains the population parameters. Okay. If you go to the class, you can see this header file defines those class. This is a definition of neural net. What is neural net contains? Step, total number of simulation steps, number of populations, and after this, and also some functions can be called by this class. Pop have more functions and variables. See, get spec current, get refactory step left, lots of C+ function. I can give you an example. For example, I don't know. Let me see which variable. How do you find out some default? Let's use adaptation as an example. If I don't know what's the default value of token, apparently it's showed here, but in some subroutines it doesn't show it. If you don't know it, how do you know that? Search this token and find out the HDFL directory. See here, it is initial 010 token. And then we copy this directory, and go to the code, C code here, the simulation interface. We search this directory. See here, this where it read this guy. See here. Then we can know what is the value name. He still used token, and then we search token in the whole folder, in this folder for the token. You should use some powerful editor like Sublime or Visual Studio editor, something like that. Just search token, and then you will see all tokens in this folder. See here, the neural pop CPP defined its default value is 80 milliseconds. See, I just give you an example. If you don't know details, use this way to find out the answer in C++ by yourself. First, determine the location of HDFL files, and then search this guy in the simu interface. Find out the variable's name in C++ code, and then globally search this variable, see its default value or the relevant code. Okay, that's it for today, my content. So any questions or things you want to know, we can discuss. So all done?
I think so.
Okay.